Good morning, Sahadi and everyone. Today, we are going to present our mini project, which is water level control system. But before that, allow me to introduce myself. My name is Mervin Benda Anak Kismet, and this is my partner, Muhammad Yazid bin Sufyan Jong. Now, before we begin, here's a quick look at the table of content for our presentation. First, we'll start with the introduction, followed by the problem statement and the objective of the project. After that, we'll move into the methodology, where we explain the block diagram, simulation circuit, and PCB layout. Next, under result and discussion, we'll cover the circuit analysis and simulation result, where we show how the system works in practice. And finally, we'll end with our conclusion to summarize the key takeaways from this mini project. Now, let us begin with the introduction. First of all, this project is developed by students of electronic design as a part of a mini project at UiTM Sarawak. Next, we have created a water level control system that are used transistor-based circuit. This system is designed to automatically monitor and regulate the water level in a tank, replacing all mechanical methods that are often inefficient. It was developed during the July 2025 semester as a part of the cost timeline and assessment requirement. Now, now, where can we use this system? It's suitable for home, farms, and industrial water tanks. Basically, anywhere that need reliable water level automation. Why do we need this kind of system? It is because mechanical systems are prone to failure. By using an electronic approach, we can improve accuracy, reliability, and ensure the system works automatically without constant human monitoring. As for how it works, we designed a signal conditioning circuit using transistor and operational amplifier. This circuit processes input from a float sensor and control a relay as an output. We also tested the design through simulation using tools like Proteus and Multisim. And lastly, our aim is to build a simple, reliable, and automated system that manages water level efficiently with minimal manual effort. But before we design the water level control system, we need to identify the problem. So, the problem states that water tanks are commonly used to store water in home, farm, and industries. However, most existing systems still rely on mechanical methods to control water level. These methods are often inefficient, prone to failure, and require regular checking. As water usage increases in daily life, agriculture, and industrial operation, this outdated system can lead to overflow, wastage, or supply issues. A better solution is to build a simple and practical electronic water level control system by using components like transistor and operational amplifier to improve accuracy, automation, and reliability. Now that we have identified the problem, let's move on to the objective of our project. Our main goal is to design and develop an electronic water level control system using transistor-based circuits that are automatically monitor and regulate water level in a tank. This system aims to be more efficient, reliable, and low maintenance than traditional mechanical method. To achieve this, we divided our project into three key objectives. First, we aim to design a water level control system. Second, using electronic components such as transistor and sensor, replacing float-based mechanical system. Second, we set out to construct a working prototype that can detect and respond to changes in water level by triggering output like LEDs or relay. Third, we plan to simulate and test the circuit using software tools like Proteus and Multisim to ensure functionality and reliability before building the real version. That concludes the introduction, problem statement, and objective of our project. Now, I'll pass the presentation to my partner, Muhammad Yazid, who will walk you through the methodology, simulation, PCB layout, and analysis of our system. Over to you, Yazid.
Next, I will explain about methodology part. First, we will go through about how the block diagram and for the system will will flow. First, of course, it will have water tank. The water tank we set have three level sensor. First is at mid, at low, at the middle, and the high. At the low sensor, if the water at the low level, it will turn on transistor at low and the LED blue on. If the water level at the middle, it will turn on the transistor at mid and the LED yellow will turn on. If the water level is full or high enough to the sensor, it will turn on the transistor high and LED red on, and it will turn off the valve to stop the water to feed in. Next is this is our circuit that we use for this system. This circuit we run at the Proteus. After that, we have a PCB layout. First, PCB at the left is a circuit for PCB layout circuit, and the right is the 3D visualizer. It's a 3D we can see in the if the PCB at the physical. We have six resistor, three transistor, three LED, and F diode, relay, valve, and a switch. Okay, next is financial management. For the price component we use is first we have transistor 2N40 at 9. We use three transistor each level, low, mid, and high. Each transistor is 30 cent and total is 90 cent. And second component we use is LED. We use three LED, blue, yellow, and red. Each LED is 20 cent and total is 60 cents. And for the relay we use 12 volt. We use one only relay and its price is 5 ringgit. For the valve we use 12 volt. We use one and valve we use each price valve is 10 ringgit. And for the battery 12 volt we use only one because we just use 12 volt battery. For the valve, each battery is 15 ringgit. And for the diode we use one N4077. We use one and each diode is 50 cents. And for the resistor we use total 6, and for the 10 kilo ohm we use 3, and for the 1 kilo ohm is 3. Total resistor is 60 cent. For the total price component we use is 32 ringgit 60 cents. Next, for the result and discussion is our circuit analysis. This is Circuit analysis, we use specification transistor we use is 2N5089, and we set AV is 20, ZI is greater than equal 10 kilo ohm, and ZO is less than equal 1 kilo ohm. Okay, we use datasheet. We use for the IC is 1 milliohm 1 milliampere, and you can see 5089 we use beta is or HFE. We use 450. We will go through the circuit analysis. Okay, we use common emitter. This is DC circuit and AC analysis. For the calculation, I use AV is equal to V over VI. VO is negative beta IBRC, and for the VI is IB R pi. We can cancel IB, and we get AV equal to negative beta RC and R pi. That is one equation, and we know R pi is equal to beta VT over IE, and we can combine 2 and 1 equation. AV equal to negative beta RC over R pi is beta VT over IE. We can cancel a beta, and we get AV equal to IE RC over VT. We know IE from the datasheet is 1 milliampere, and for the VT is 26 millivolt, and the AV we get from the ice and from the specification is 20. 20 equal to 1 milli RC, and equal no no over 26 milli, we get RC is 520 ohm. Okay, next we will find for the RB resistor at base. We use KVL. You can see at the DC circuit, negative VCC from the at the top, negative VCC IBRB plus VBE equal to 0. We set VCC is 12 because we use VAF 12 volt. Negative 12 plus IB we can find from the IB equal to IC over beta. IC is 1 milli, beta we get from datasheet 450. We can get for the IB is 2.22 microampere. Okay, we know for the IB, we can put the IB from for in the equation at KVL. Negative 12 plus 2.22 micro RB plus 0.7 is for VPE. It's a common for VBE. Uh, for for BJT for BJT. Okay, we know that we can get that RB is equal to 5.09 mega ohms, and now we get RB and RC. Now we want to find ZI and ZO for the specification. For the ZI, it is we can find ZI is RB parallel with R pi. Okay, now we don't know R pi, but we can find it. R pi equal to beta VT over IE. Beta is 450 from datasheet, and VT is 26 milli over IE from datasheet also. And for the R pi is 11.7 kilo ohm. We parallel it 5.09 mega parallel with 11.7 kilo ohm is 11.673 kilo ohm. ZI is meet for the specification because specification need ZI greater than 10 kilo ohm. For the ZO is equal to RC, and RC is 520 ohm. It also meet for specification because ZO need less than 1 kilo ohm. Okay, for the E12 standard, we say it get RB is equal to 47 mega ohms and RC is 560 ohms. Okay, that's all for the circuit analysis. Okay, now we can see we want to see how The calculation is same with the simulation. We simulate it multi-sim. First, we can see for the simulate at interactive, the prop one, we want to see the IB. IB is before in calculation is 2.22 micro, but in the simulation, we get 2.16 microampere. And for the prop 2, we can see for the IC, and in simulation IC is 2.03 milli. We can get IC from datasheet is 1 milli. It's approximately same. And next is we simulate for AV gain. We simulate AV gain with multisim at the SC sweep, VO over VI. We get AV is 36.13. Uh, it's same because we we set AV is equal to 20. It's approximately same. This is our simulation result. I will show you. We have three conditions: low, middle, and high condition. For the first condition, we have water. If the water tank at the low condition, it will turn on the switch. You can see at the blue arrow. It act like a sensor water, but in the Proteus, we act like a switch. Okay, you can see the switch. It switch to the low transistor. If the water level at the low, it will turn on the LED. It will turn on the transistor at the low, and the LED blue with it will turn on. And the switch at the relay also turn on. Okay, next is for the second condition at the middle. It will turn on the switch at the middle, and it will turn on the transistor, and LED yellow it will turn on. And for the valve, for the relay at the red arrow, it will turn on, still turn on. Okay, for the last condition is at the high condition. If the water is full, the transistor at the high, it will turn on, and LED red turn on, and the valve and the relay is turned off. We can see at the switch at the relay at the red arrow, it turned off to the another condition, another side.
Finally, we have reached our conclusion. In conclusion, this mini project has successfully demonstrated the complete process of designing, constructing, and simulating an electronic water level control system. A signal conditioning circuit was developed using transistors and operational amplifiers to accurately respond to sensor input and control a relay for valve management. This system was designed as a modern replacement for conventional mechanical method, offering enhanced precision, reliability, and automation. The simulation result obtained using Proteus and Multisim has validated the functionality and effectiveness of our proposed design. All above, this project has significantly deepened our understanding of circuit design, principles, signal processing technique, and practical application of electronic design automation tools. That would be all from us. Thank you for your kind attention and patience throughout the presentation. We look forward to the future opportunities to share and learn together.